Hey guys, welcome to this video on the 2020 year 13 physics for rotational kinematics and simple harmonic motion. So this is the test number 1, and let's get straight into it. So question 1, rotating turntable. A solid wooden turntable that has a mass of 15 kilograms and a radius of 1.5 meters has a metal block of, mass 18.4 kilograms, placed 1.2 meters away from the center. A constant torque of 125 newton meters is applied at the extreme edge of the turntable until it attains a constant angular velocity of 26.4 radians per second, starting from rest. At this instant, the torque was removed and the system rotated freely with negligible friction. Whereas we know that the inertia for our point mass is I equals to mr squared, and we know that the rotational inertia for our turntable is 2 over 5 mr squared. So question A, show that the rotational inertia of the system is 40 kilogram meters squared. Right, so for this question, our rotational inertia of the system will be the total of the rotational inertia of its individual components. So we're going to be adding the rotational inertia of the turntable to the rotational inertia of the point mass with respect to the center of rotation, which would be the center of the turntable. So in this case, we have our rotational inertia, so our inertial total, is equal to inertia of our point mass plus inertia of our turntable. So inertia of our point mass is I equals to mr squared, so IP equals to mr squared, and this equals to 18.4 times 1.2 squared, because this block is 1.2 meters from the center of the circle, and I just realized this arrow is in the wrong place. Apologize. Yeah, that distance is 1.2 meters. So we should get, this one should be 18.4 times equals to 26.496 kilogram meters squared. And the rotational inertia of our turntable would be 2 over 5 mr squared. And this equals to the mass of our turntable, which is 15 kilograms, times 2 over 5 times 1.5 squared. Right, so 15 times 4. Right, so that comes out to be 13.5 kilograms meters squared. So our total inertia would be equal to the sum of both of these inertias. So we get our total is 39.996 kilogram meters squared, and that is about 40 kilogram meters squared if you round it to one significant figure, actually, so that's just 1 SF. And this should just be a common achieved question here. Right, question B. For how long was the torque applied to attain the angular velocity of 24.6 radians per second? Alright, so we're told that the average torque is applied. So that means if there's a torque applied, then there has to be an angular acceleration, because it is an unbalanced torque on the extreme edge of the turntable. Because it is a constant torque, that means we're also going to have a constant angular acceleration. And the magnitude of that angular acceleration depends on the magnitude of the torque and the total rotational inertia of the system. That's because the rotational inertia is actually defined as how well an object can resist a change to its angular velocity, which is angular acceleration. Alright, so for this one, we're going to be finding our average angular acceleration, and using this average and using our rotational kinematic equations in order to find the total time it takes for the angular velocity to go from 0 radians per second to 24.6 radians per second. So we can say that our torque equals to our inertia times our angular acceleration. We know that the average torque applied is 125 newton meters. That equals to 40 times of angular acceleration. So we should get that if we rearrange the equation, we find that our angular acceleration equals to 3.125 radians per second. Alright, so at this stage of the question, we know that we have to use our rotational kinematic equations. So the easiest thing to do right now is to write down on the page all the information you have. So we just worked out that our angular acceleration is 3.125 radians per second. We are trying to find our time, so we put a question mark next to our time. we know that our initial angular velocity is actually 0 radians per second, and we know that our final angular velocity is 24.6 radians per second. Right, so looking at this, okay, so at this stage you can go to your formula sheet to find which equation has both 4 of these variables, but you should find that that equation is final angular velocity equals to initial angular velocity plus angular acceleration multiplied by time. So we can multiply our, we can plug in our values in order to rearrange and find for our time. So we know that our final is 24.6 radians per second. That equals to 0 plus 3.125 t. Alright, so if we rearrange for time, we should get an answer of 24.6. Alright, so we should get an answer of negative. Yes, it should be negative. Negative. Oh, shouldn't be negative. What am I doing? Sorry. Time is actually. Apologize. Sorry, it should be time should be equal to 7.872 seconds. Sorry about that. Did not mean to say it was negative. Time cannot be negative, so apologize for that. So time is 7.872 seconds. So looking at this at the above values, we can see that our lowest SF is actually 3 SF in the question, so that's the significant figures that we're going to round to. So as you can see here, our time right now is in 4 significant figures. We have to round that down to 3 significant figures. So we'll just drop the last 0.0, we'll drop the last 2. We get our time equals to 7.87 seconds, and you can say that is 3 SF. Alright, so this question should be a merit level question. In terms of getting an achieved, if you can able to find the angular acceleration, that should be enough for an achieved. Question C. While the system is rotating at 24.6 radians per second, a small amount of water of negligible mass is put onto the turntable, which causes the metal block to slide outwards towards the extreme edge. Alright, so it tells us that the amount of water is negligible mass, which means that it has a negligible rotational inertia. Because if the water had a rotational inertia, that's going to actually increase the rotational inertia because we're adding to the system. But for us, it's a negligible mass, which means that it has negligible rotational inertia. So question C tells us to explain how the angular velocity changes as the metal block slides outwards. Right, so this is actually a very common NCAA question. So in terms of this question is the metal block is sliding outwards, and as a system, the center of mass of the system is actually getting closer to the extreme edge of the turntable, and the distance between the center of mass and the center of rotation. The center of rotation is the center of the turntable, so the distance between that center of mass and that center of rotation is actually increasing. Because it's increasing, actually the rotational inertia of the system is also increasing. What we do know is that the movement of this metal block towards the out of the extreme edge doesn't apply like any external unbalanced torques onto the system, and because there are no external unbalanced torques, and we're assuming that the friction is negligible, which means that also the friction is not resulting in any external torques, so we can actually say that there are no external torques acting on the system. And we can link this to that the angular momentum of the system will not actually change. Because the angular momentum doesn't change and the rotational inertia of the system has actually increased, that means that the angular velocity has to decrease because rotational inertia is defined as an object's ability to resist change to angular velocity. Okay. So in terms of writing this in words, we can say that as the block slides outward, the center of mass of the system is now further away from the center of rotation of the system. And you can say that the center of rotation is the center of the turntable. So center of rotation is center of turntable. Alright, so we can say that this means that the rotational inertia of the system, the rotational inertia of the system will increase. Okay, so you can link that to a formula. So you can say that this means that the rotational inertia of the system will increase because I equals to, you can't say I equals to anything in this case. You just say I is proportional to R squared. Hence, as R increases, that means I must decrease. R increases, I must also increase, must also increase. Alright, so now we can say that, so the extreme edge, so now we can link this to the angular velocity of the system. So we can say, first we link it to, because the angular momentum is not changing, so we can say the sliding of the block causes no external torques on the system. And because friction is negligible, there are no external unbalanced torques in the system. By conservation of momentum, by conservation of angular momentum by conservation of angular momentum, the angular momentum of the system must remain constant. So by no but the angular momentum means that the angular momentum will stay the same. Because the rotational inertia has increased, we can say the angular velocity must decrease. And you can link that to a formula. You can say that angular momentum equals to inertia times of angular velocity. So therefore, because the momentum is constant, you can say that inertia is inversely proportional to angular velocity. Hence, as inertia or rotational inertia has increased, angular velocity must decrease. Alright, so that will be your answer to this question. This question should be a merit level question, and to get an achieve level grade, if you can link it up to the rotational inertia increasing with justification, you should get an achieved. So okay, so probably from here to here will get you an achieved grade, or Yeah, I think that would be the most confident for the achieved grade. So being able to justify that the rotational inertia of the system has increased, that should get you a confident achieved grade there. Alright, question D. Calculate the angular velocity of the system when the metal block is slid to the extreme edge and discuss what happens to the velocities of the turntable and the metal block when the block falls off the turntable onto the floor. Alright, so we'll start off by calculating our angular velocity of the system. So we know about our inertia before, so let's put in black pen. So our initial inertia was 40 kilogram meters squared. And we know that our initial angular velocity was 26.4 radians per second. So we can use this information to calculate our initial angular momentum. So we know that angular momentum equals to inertia times angular velocity. So momentum equals to 40 times 26.4. That's our initial momentum. So 40 times 26.4 gives us an answer of 1056 kilogram meters squared per second. So now we need to calculate our new inertia. So our new inertia, again, the rotational inertia of the system is equal to the sum of all the individual rotational inertias of each component in the system, okay? So our final rotational inertia equals to our inertia of the turntable plus inertia of the point mass. Inertia of the table actually stays the same because it is still the same table, so we can say that was equal to 15 times 1.5 squared, and that multiplied by 2/5, and that was 13.5 kilograms meters squared. And we know that our inertia of our point mass has increased because it's slid further away from the center of rotation, so that is equal to m, which is 18.4 times 1.2 squared. Alright, that's not 1.2, it's 1.5, apologies. 1.5 squared because it's moved to the edge. So times 1.5 squared. Alright, that gives us our inertia is 41.4 kilograms meters squared. You add them together, you should get 44.9 kilograms meters squared. Let me double check that. So 49. 44.9, that's right, okay. Is that 44? Let me double check this. What, 18.4 times 1.5 squared? 41.4. Oh, sorry, that's 54.9. What am I doing? Sorry, guys. Dreaming. Okay, so 54.9 kilogram meters squared. And now we can use this information to calculate our final angular velocity. So we can say that angular momentum is conserved. So therefore, we can say that final is equal to our initial, and therefore we can say that 1056 equals to 54.9 times of our angular velocity. So should get an answer here of, okay, so our angular velocity comes out to be 19.23 radians per second, and we need to round that down to 3SF because that's the lowest significant figure given by the question. So we'll drop the last 3 and we'll get 19.2 radians per second, and that's rounded to 3SF. Alright, so now we need to explain what will happen to the velocities of the turntable and the metal block when the block falls off the turntable onto the floor. Alright, so when the block falls onto the floor, well, when it falls off the turntable firstly, when it actually falls up, it actually has its own angular momentum, so a component of the angular momentum, so it's still a system. So that means that actually when the block falls off, the angular momentum and the angular, sorry, what am I saying? Okay, so when the block falls off onto the floor, the angular momentum, the block has its own angular momentum, and turntable has its own angular momentum. And what actually happens is that because there's a component of the angular momentum on the block, that actually means that the angular velocity of the turntable will not change, and the angular velocity of the block will not change either. Okay, so if we put that into words, we can say that when the block falls off the table, when the block falls off the table, the block has its own angular momentum. And that can actually be expressed as L equals to mvr, because not mv squared, mvr. Because when the block falls off, it's going to be assuming it falls off linear in a linear direction, it's going to have an angular momentum given by mvr, and the r is with respect to the center of rotation point of the turntable. Because of this, the angular velocity of the turntable and the block won't change. So you can kind of look at it that when the block falls off the turntable, you can look at the turntable by itself and the block by itself. So because the block is now gone, the rotational inertia of that turntable has decreased. However, the angular momentum, the block has taken a component of the angular momentum away from that turntable, which means that the angular momentum of that turntable has also decreased. And these two are actually the change is directly proportional to each other. So therefore, the overall net change of the angular velocity is none. So what actually happens is that the angular velocity doesn't change at all, because the angular momentum decreases, but the rotational inertia decreases as well. So these decreases by the same proportional amount. So therefore, because they decrease at the same proportional amount, there is actually no change to our angular velocity. So you can say that, what can we put this into words? Because of this, angular velocity of the turntable and the block won't change. This is because not angular, the rotational the rotational inertia of the turntable decreases, and that's because we're not considering it, because it's because the block falls off, the rotational inertia of the turntable decreases. Due to the block falling off. Because the block takes the component of the total angular momentum. And angular momentum. Hence, angular velocity doesn't change. Alright, so that should be the full answer to this question. So if you get everything, so both the calculation and the explanation, you should get an excellence level grade. To get a merit level grade, if you can get this calculation, I'm thinking you could get a merit grade, or if you have a very good explanation, I believe you can also get a good merit grade. To get an achieved, I think if you can find the probably up to this part here, maybe will get you an achieved, or having a brief explanation by itself might also get you an achieved. I'm not sure because I don't have the marking schedule as of this current stage. Alright, so question 2. A diver of mass 55 kilograms is to perform a backwards 1.5 somersault from a diving board as shown in the diagram below. Assume the mass of the diving board is negligible. The sagging of the board is also negligible when the diver stands at the end. Before executing the dive, she tests the board's springiness by pumping it with her legs. She finds that she can build the largest amplitude of oscillation when the interval between her regular pump is 1.2 seconds. She notices that if she makes the amplitude any bigger, she will lose contact with the board. She is making the board oscillate at such an amplitude that she is on the point of losing contact with it. This means that her maximum safe acceleration is g equals to 9.8 meters per second. Question A. Show that the vertical spring constant of the diving board is 1,510 kilograms per second squared. Alright, so for this question, we're going to be using the period of oscillation of a spring, which is, so we're considering this diving board as a spring right now. So we're going to say that period equals to 2 pi square root of m over k. And you can find this formula at the back of your, formula sheet. So we know t, so our t was 1.2. So 1.2, because that's the intervals of the pump, so that's 1.2 equals to 2 pi square root of m, which is 55 over k. So therefore 1.2 divided by 2 pi squared equals to 55 over k. So therefore k equals to 55 over 1.2 over 2 pi squared. Right, so 1.2 divided by 2 squared. Right, so that gives us a k value of 1,507.86 newtons per meter, and that gives us 1,510 newtons per meter if we round it to 3SF. And this is definitely just an achieve level question. Show that the amplitude of the simple harmonic motion is 0.57 meters when she is on the point of losing contact with the diving board when pumping at 1.2 second intervals. Alright, so in order to ensure that she doesn't lose contact with the diving board is to ensure that her maximum acceleration is always below the acceleration of gravity. As soon as her maximum acceleration is greater than the acceleration of gravity downwards, that means that there will be a net acceleration upwards, and that means that when she is traveling upwards, she will lose contact with the diving board. Even if it's slightly above 9.8, she will still have that unbalanced net acceleration, and that's going to lead her to have a lose contact with the springing board. So to ensure she doesn't lose contact, it's to ensure that her maximum acceleration is equal to or less than 9.8 meters per second squared. Alright, so we know that our maximum acceleration is equal to AW squared. Alright, so the reason that that's the case is because normally we can say that A is equal to AW squared, A omega squared cos of omega t, or A is equal to A omega squared, that's pretty sure it's negative, sine omega t. Alright, so the reason that the maximum acceleration is A omega t is because in a cos or a sine graph, let me just draw a quick sketch here. So a cos graph starts at 1 and kind of goes like, it oscillates between -1 and 1, and a sine graph starts at 0 and does the same, oscillates between 1 and -1. Okay, it's a bit of a messy drawing, but my point is that the maximum and minimum values of the sine and the cos graph is 1 and -1. At the maximum acceleration, this cos omega t or sine omega t, that's going to be equal to 1. And because at this maximum, cos omega t and sine omega t is equal to 1, 1 times of anything is just that, anything, right? So negative a omega squared times 1, that's still negative a omega squared. So that's why we say that our maximum acceleration, so that's our maximum acceleration, equals to amplitude times omega squared. So all we need to do here is to plug in 9.8. That's our maximum acceleration that we cannot go over. And that is equal to our amplitude, which we do not know, times of omega squared. However, we do know that omega equals to 2 pi f, and we know that f equals to 1 over t. So if we plug 1 over t as f, we'll get that omega equals to 2 pi over t, and we know t equals to 1.2 seconds, so we'll say that omega equals to 2.5 over 1.2. 2 pi over 1.2. Alright, so that's about 2.236 radians per second, or you can just leave it as per second, doesn't really matter. So omega equals to 5.236 radians per second, so we can plug that in for our omega. So 9.8 equals to a times of 5.236 squared. So 9.8 divided by... Alright, so we get our amplitude comes out to be 0.35746 meters. And if we round that down to 3SF, we'll get A equals to 0.357 meters, 3SF. Alright, so this question should be a merit level question. I'm thinking it should be a merit level question. So if we can get up to here, that would definitely, or most likely, get you a merit grade. To get an achieved grade, if you can find the angular frequency, I think you could get an achieved grade. I'm not sure though. That you might be able to get an achieved grade, but not 100% sure there. Right, question C. Explain why she is able to maintain her large amplitude with minimal effort for when the interval between regular pumps is 1.2 seconds. Alright, so this is because the regular pumping at 1.2 seconds happens to be, the frequency of these pumps happens to be equal to the natural frequency of the system. So the system is made up of the board. It's made up of the board and the diver. And that's the system. So we know that the natural frequency of the system is equal to this pumping frequency that is being exerted by this diver. Because they are equal, because the natural frequency and the driving force frequency are equal, this is going to cause a very large amplitude of oscillation, and that the diver does not even need to put a lot of effort. So the diver doesn't need to apply much force, but the large amplitude can still remain very large because of this resonance. Okay. Alright, so just to demonstrate what I mean is if we draw a graph real quick. So this is, if we say f0 is our natural frequency, so f0 is natural frequency, and this is our frequency on our x-axis, and we have our amplitude on our y-axis, so amplitude. Alright, so you should see that a graph should look something like this. So as you can see here, at this natural frequency, we have our maximum amplitude. So in this case, the diver is applying a force at the natural frequency, which means that it's causing a very large amplitude of oscillation. And that means that she actually doesn't need to apply a lot of force in order to achieve this very large amplitude. So this effect is called resonance. And if you look into it a little bit more, if you type up, there's actually been cases of where a bridge has collapsed because of like the wind and the cars having the cars were exerting the force at the natural frequency, which causes the bridge to oscillate very, very rapidly and very large amplitude, and eventually the amplitude of oscillation was so big that the bridge actually collapsed. So you should be able to find some videos on that if you're interested. Like, just search up bridge collapse resonance, and you should be able to find a couple of instances. I think there was a US bridge that collapsed, and and somewhere in Japan where a bridge collapsed, and that was because the driving force frequency was equal to the resonant frequency, and this caused the bridge to oscillate a very large amplitude until the support forces weren't able to handle that oscillation anymore, and it just collapsed. Alright, so similar in this case as well. So if we put this into words, okay, so we can say that the diver is able to maintain a large frequency, not frequency, a large amplitude, of course, amplitude, because the frequency of her pumps is equal, or not necessarily equal, you can just say it's very similar. It's very similar to the natural frequency of the system. This can achieve very large amplitudes. Without applying Alright, so that should be your brief explanation. If you want to go a bit further, you can say that the natural frequency, you can say natural frequency depends on the physical quantities of the system. So what I mean by that is, e.g., what the material is the plank made of, what material. Okay, so even if the different mass diver is jumping on the board, that's also going to have a different resonant frequency. So you can say different diver. You can say, well, just physical quantities that can possibly, only the physical quantities can change the natural frequency of the system. So you can add that in, but I don't think it's necessary. The diver is able to maintain a large amplitude because the frequency of her pumps is very similar to the natural frequency of the system. This means that the diver can achieve very large amplitudes without applying much force, minimal effort. Guess you can further support your answer with that graph I just drew. I think in this case is very relevant. So frequency, so I should look. Right, so this is the graph I drew. So you can say, as seen on the graph, when the driving force is very similar to the natural frequency, this is when there's going to be a very large amplitude of oscillation produced, even though there is minimal force produced. So you can say something like that to justify your answer. To further justify your answer, you don't have to, but you can say, you can find the frequency very easy. So frequency is 1 over t, 1 over 1.2 should give us our frequency. So you can say that our frequency is 0.883 hertz. So then you can say that the natural frequency of the system is very similar to 0.833 hertz, which means that the driving force from the diver is being applied at a similar frequency to the natural frequency, which causes the very large amplitude of oscillation. So just linking all of these points together should be sufficient. But perhaps just statements here should be enough to get you a merit. But just for during the exam, if they ask you something about resonance, it really doesn't hurt for you to draw a graph. It's just like a quick sketched amplitude over frequency, and your F0 represents your natural frequency, and it looks like a very sharp bell curve. And it's very good to justify your answer and to add more evidence of understanding that can actually get you access you to higher grades. Yeah. So this should be a merit level question. To get an achieved, for an achieved, I think you can just get up to here. You can just say that she is able to maintain a large amplitude because the frequency of her pumps is very similar to a natural frequency. I think that should be enough for an achieved, actually. That's just a simple statement to say that the amplitude is large because the natural frequency is very similar to the driving force frequency. So that should be enough. Alright, so looking at question D now. On the axis below, draw a graph showing the total energy, the kinetic energy, and the potential energy of the diver changes over displacement relative to the equilibrium point when the interval is 1.2 seconds. Label all the intercepts and the points of intersection with correct numerical values. Alright, so they want both the kinetic energy and the potential energy of the diving board. Okay, so you know that the energy of the kinetic energy and the potential energy at any one point has to sum to the total energy. So the total energy is always going to be constant, assuming there is no dampening. Okay, so dampening is the effect of when energy is lost during oscillation to heat and sound. So in this case, you can say that we're assuming that the heat and sound energy, none of that energy is lost, so that the energy of the system is always the same. So so we just write down that assumption. So say assume no dampening. Because if there is dampening, then the total amount of energy will decrease over time, and the amplitude of oscillation will also decrease over time if there is dampening. So we're going to assume there's no dampening, which means we can immediately draw our line for our total energy. It's just going to be a straight line here, because it's also always going to be constant. A straight line represents our total energy. So alright, so this is our line. We can say that this is our energy total. Right, so now we need a link. Now we need to draw our graph for the kinetic energy and for the gravitational potential energy. So we know that the kinetic energy will always be at the maximum at the equilibrium, because that's when she is bouncing on the diving board at the equilibrium, that board is going to be traveling the fastest. So that's when the kinetic energy is at the maximum. And we're going to take our reference points in terms, so we know that when the plank is straight, there are no elastic potential energy stored. So that's when the plank is straight, and that's when the displacement is 0. So at the equilibrium, the displacement of the plank is 0 meters, which means there are no potential energy, but we know that the kinetic energy has to be at the maximum. So in this case, we know that energy total equals to EK plus EP at any moment. So we know that at the equilibrium, EP is 0. So that means EK must be equal to ET. So we'll immediately note that down. So because this question doesn't exactly tell us at which point to start, I think we should also write that down. So we're going to assume we are starting at equilibrium. So equilibrium start, okay? So at the start, we're going to have a maximum kinetic energy, but we're going to have a minimum, so 0 gravitational potential energy. So then we're going to be looking at the maximum displacement. So at the maximum displacement, we know that at the maximum displacement, the board actually pauses for a very brief moment. So at the maximum displacement, there's actually going to be no kinetic energy, because it's actually temporarily stationary. So 0 kinetic energy, which means that all the energy has to be purely in the form of elastic potential energy. So at the okay. I just realized something. So this is so x-axis is displacement, our y-axis is energy. So displacement, okay, so this is actually 0, this is negative, and this is maximum. So apologize, guys. So at the equilibrium, we're actually starting at 0. So this is where we start. At the positive maximum displacement, we're going to have a maximum potential energy and a minimum kinetic energy. So same goes for the negative displacement. Okay, so our line for the kinetic energy, it's going to be maximum at the maximum displacement. So it's going to look like a parabola here. Similarly, for our potential energy, it's also going to look like a parabola, but it's going to be reflected parabola. So it's going to start at the maximum, it's going to decrease to 0, and it's going to rebound back up to the maximum at the maximum displacement. So this is a graph where it should look like, okay? So now we need to label all the intercepts and the point of intersection with correct numerical values. So if we label all the points of intersection, so we can say that this point here would be negative displacement, so maximum negative. It tells us, does it tell us the, yeah, so our amplitude is 0.375 meters, so this is negative 0.357, and this is 0. Similarly here we have 0.35 meters, and this is equal to EK, which we should figure out. So EK, we should figure out our total energy. So total energy would be equal to EK equals to half mv squared. We know V equals to AW because this is our maximum velocity, okay? So EK equals to half a squared omega squared. Right, so if we get these values, we have our EK equals to 1/2, mass is 55, A is 0.375 squared, times of omega, which was, what was that omega? 5.236 squared. 5.236 squared. Right, so 55. Right, so our total our total energy is 96.088 joules. So if we label this intercept as 96.088. Alright, similarly here we have our displacement is 0, 96.088 joules. And here would be 0, 0. So at this top point here, we're going to have our maximum positive displacement, which is 0.357, and our maximum energy, which is 96.088. At this positive displacement here, we're going to be positive displacement, and we're going to have 0 joules. Alright, sorry, this is 0.375. Alright, so that's the outer edges of the intercept labeled. So now we need to label this intercept and this intercept, which is slightly harder because we need to derive some formulas for the kinetic energy and the and the potential energy. Alright, so we know that our kinetic energy equals to half mv squared, and our total energy, equals to half mv squared, but our v is our maximum velocity, so that will be at equilibrium. So ET equals to half m a squared omega squared. That's going to be our total energy in the system. So ET equals to half m amplitude squared omega squared. Alright, so we know that our EK at any point is half mv squared, but in this case v would be AW cos omega t, and this is assuming that we're starting at the equilibrium. Okay, if we're not starting at the equilibrium, if we're starting at the maximum displacement, then it won't be a omega cos omega t, but we're assuming that it starts from the equilibrium. Both ways will give us the same answer at the end, so this is just an assumption. So EK equals to half m a squared omega squared cos squared omega t. Alright, so we know that our ET minus EK equals to EP. So therefore half m a squared omega squared equals to half m amplitude squared omega squared cos squared omega t, which equals plus EP. Therefore half m a squared minus half m amplitude squared omega squared cos squared omega t, that equals to our EP, And going on to the next page now. Now we can actually factorize. We can say 1 minus cos squared omega t multiplied by 1/2 a squared omega squared. Let me check that. Right. So, okay. So we can take one. We can take 1 minus cos squared omega t and this 1 here. Yeah, and we can factorize it out. That is equal to our EP as well. So this is equal to EP. We know 1 minus cos squared omega t, that equals to sine squared omega t times of 1/2 m a squared w squared. Alright, so we know that what do we do from here? Equals to EP. Alright, so we know that y equals to sine omega t. Well, sorry, a sine omega t, apologize. So we know y equals to a sine omega t, and we have this a squared here and this sine squared omega t here. So y squared equals to a squared sine squared omega t. And we can actually substitute this in terms of a squared sine squared omega t in our equation. So we can say that 1/2 m omega squared y squared equals to EP. And that's because sine squared omega t times a squared is actually our displacement. So now we have an expression for EP. So EP equals to 1/2 m omega squared y squared. And we have ET equals to 1/2 m a squared omega squared. And we have EK equals to 1/2 m v squared. Alright, so now we need to find when at what point is both the EP and the EK are equal. So in this case, we can say that because we know that our total energy equals to our EP plus EK. So we know that ET minus EK, that equals to our EP. We know EP is equal to 1/2 m omega squared y squared. We know that our total energy is equal to 1/2 m amplitude squared omega squared. And we also know that our EK at any point, so this is EK at any point, we know that that is also equal to 1/2 of, so we know V equals 2. But A is at any displacement Y. At any displacement Y, so therefore EK equals to 1/2 W squared Y squared. Okay, so now we can write our formula up. So we can say that 1/2 MA squared W squared minus 1/2 W squared Y squared equals to EP, which is 1/2 M W squared Y squared. If we move this 1/2 omega squared Y squared to the other side, it will become 1/2 MA squared omega squared equals to M omega squared Y squared. If we cancel m omega squared on both sides, we'll get a squared over 2 equals to y squared. A squared equals to 2y squared. And therefore a equals to root 2y squared. And that equals to root 2y. Root 2y, that's a squared over 2 times 2. Right, so amplitude equals to root 2y. That's right. But if we want in terms of amplitude, we can also have a squared over 2 equals to y squared. And therefore a over root 2 equals to y. And therefore if we multiply both by root 2 over root 2, that equals to a root 2. a root 2 over 2, which equals to 1/2 a root 2. Alright, so we know that the graphs will intersect at this point of of amplitude times root 2 over 2. So that's actually the point of intersection of here and here. So this is actually a over 2 root 2. So this is negative, and this would be positive a. Alright, so we know that a equals to 0.357 meters. So if we plug that into as a, we'll have 0.357 times root 2 over 2. So we should get that this one is 0.2524 meters. And this would be, on the other hand side, will be negative 0.2524 meters. Right, and that's it for labeling this graph. We have labeled all the intercepts and we derived the formula, so this should all get us an excellent level grade. To get a merit level grade, not too sure on this one. It's a pretty tough question to see. Okay, so for an achieved grade, if you can find this energy, this definitely can get you at least an achieved. If you can draw up a rough, the shape of the graph is correct, I think that can also get you an achieved. If you can draw up the graph and find the EK and label these boundary points, that can also get you a merit grade in my opinion. But you need to label the intercepts, all the intercepts, you have to draw the graph, and you have to find the EK in order to get your excellence level grade. Alright, so thank you for watching this video, and I hope you enjoyed, and I hope to see you all in the next one.